All right, hi, this is the fourth lecture for Math 114, 1114. Today is section 5.3, and this is the fundamental theorem of calculus. So if you guys remember when you were learning about derivatives, you learned, the long limit way first. That was really difficult to calculate. And then after that, you learned a much faster way to find derivatives. That's what's going to happen today. We're going to find a much faster way to calculate integrals. But we're going to do that by actually developing a couple of theorems that relate integrals to what we already know about derivatives. So the first fundamental theorem of calculus. This theorem, the fundamental theorem of calculus, is split up into two different pieces, the first and the second. So here's the first one. The first fundamental theorem of calculus, to understand it, first we have to understand what's called an area function or an accumulation function. So this function, capital A of x, is the integral from a up to some x value, where x can change, of some given function. So this looks like this. So I'm going to, right now, this is the area, this graph right here is the graph of f of t, right? And this graph right here is the graph of a of x. It's the area under f of t between -1 and wherever it is that our x value is. So a of x is the area from -1 up to x of f of t dt. So as we move the x value, you see we get more and more area, and so the area function is going up. And then if you see what happens right here, as little f of t goes below the axis there, then the area we're adding, remember the integral there is negative. So the accumulated area function, the net area there, is actually decreasing. And then as we keep going, once we cross the x-axis there and have positive area again, our area function is increasing. So do you see how we can make an area a function from the integral by saying it's the area from some fixed place up to some moving x value? All right, so now let's look at this and see if we can find a relationship between our function and the area function. So right here at the beginning, if we add just a little bit, if we move x just a little bit, we've added quite a bit of area, right? So the area function should be growing pretty quickly. But then if we go over, down here where it's shorter, and we move the x value the same amount, we've added a lot less area. And so that means that the area function should be growing slower. So what's the rate of change of an area function? Rate of change. What does it mean to find the rate of change of a function? Well, exactly. That's exactly what the derivative tells you, right? The slope of the tangent line, the rate of change of the function. So we seem to be saying that there should be a relationship between the height of little f of t and the derivative of the area function. The taller f of t is, the faster the derivative should be changing. The higher, the faster a of x should be changing, so the derivative should be bigger. So if f of t is big, it's high, then the area is going to be changing quickly, which means that the derivative is going to be big. So there's kind of this direct relationship between how high f is and how big the derivative is for the area function. And what this is making us think is that there should be a relationship between little f and the derivative of a. And in fact, there is. That's the first fundamental theorem of calculus. It says that if you take this area function and you take its derivative, so the derivative of the area function gives you back the same function you had before. The only thing that changes is instead of your function being in terms of t, you've changed it into something in terms of x. But otherwise, it's the exact same function. So if you take an area function and then you take the rate of change of that area function, you get back what you started with. All right, so let's look at if we can convince ourselves that this makes sense mathematically, based on what we mean when we say an area function and what we mean when we say a derivative, right? So let's look at this nice picture here. Right here. All right, so this picture is showing us that if we look at, in general, we'd be looking at the area from A up to X. This is the area function evaluated at X. And we're going to compare that, so that would be with the area function evaluated at X plus H. So what's the difference between those? Right? The difference there is this extra area right here. So that black area, that is the area evaluated at X plus H minus the area evaluated at X. Does that make sense? All right, so now let me show you that. This is the area at X. There's the area at X plus H. So that difference there, remember that's the area of X plus H minus the area of X. And let's compare that with just a rectangle for H times F of X. So this black area, that was area of X plus H minus area at X, is very close to the area of that blue rectangle. And we can find the area of that blue rectangle very easily. It's the height, which is F of X, times the width, which is how far is it from X to X plus H? It's just H. So this is H times F of X. All right, so these are going to be really close if H is small. And in fact, if we divide by H, we get the area of X plus H minus the area of X over H is approximately F of X. And then if we take a limit as H goes to 0, then as H goes to 0, the area of the rectangle is going to become exactly this area of this black outline shape. So with the limit, we actually get an equal sign. And what is this? Well, the limit as H goes to 0 on this side, there's no H, so this is just F of X. And on this side, we have the limit as H goes to 0 of A of X plus H minus A of X over H. That's just by definition. That's the definition of the derivative, remember? So that's A prime of X. So what we've just said is that A prime of X is equal to F of X. Let's take a picture of that and save it for our notes. So this is a good reason why, like mathematically, you would think that these two things should be the same. It's not a rigorous proof, and there is a rigorous proof in your book if you want to read that. But this is a good understanding of what's kind of going on. All right, so let's try applying this. Let's try applying this theorem. So what this theorem is saying is, if I want to take the derivative of an area function, so this is an integral from 3 to x, from a number, fixed number to x, of some function, so here's my function f of t, I should get just back my exact same function, only f of x. So all the t's switch to x's. but otherwise nothing changes. That's what the theorem says. It's saying it should be that easy. Let's check and see if they're right. Let's find the actual area function. So the area function, well, actually, this sounds really hard. We'll do this at the end. I'm going to come back to this page. Try to remember. We'll see if we can figure out if they're actually right, because we're going to learn that easier way to find integrals. And then we'll take the integral and then we'll take the derivative and see if we get back what we started. All right, so this is just saying, for now, that anytime you're going from a constant up to x of an area, and then you take the derivative, you get back what you started. So you notice t cubed plus 5t became x cubed plus 5x. All right, so let's try it again. It says the derivative from y to 6, the derivative in terms of y, from y to 6 of t cosine of 6t plus 11 dt. So can we just write the answer? Can we just replace the t's with y's? Close, but not quite. I mean, the fact that they're y's doesn't really matter. But in the theorem, it says you have to have the variable on top and a number on the bottom. We have a variable on the bottom and a number on top. Is there a way to switch those? Is there a way to put the 6 on the bottom and the y on the top? Yeah, that was one of our properties of integrals, right? If we switch them, we're allowed, we just have to put a negative sign out front. And then if you're taking the derivative of a negative something, you can just pull that negative sign out front of the derivative. So now we have the derivative of the integral from 6 to y of t cosine of 6t plus 11 dt. Now we can use the theorem right here, and we get, just replacing the t's with y's, y cosine of 6y plus 11. Does that make sense? Okay, let's try again. Now we have the derivative in terms of x of the integral from negative 11, so that's a constant like we need, to x to the 5th of e of t tangent of 3t dt. So can we use the theorem on this one? Everything matches except the x to the 5th, right? I mean, we have a derivative, we have a number on the bottom, we have a function in terms of t, but we're supposed to have x, and instead we have x to the 5th. So what do we do about that? Well, let's remember what we would do about that in a simpler case. So if you were going to take the derivative in terms of x of something like sine of x, well, that would just be cosine, right? Cosine of x. But what if you were supposed to take the derivative in terms of x of sine of x to the 5th? What do you do about the fact that that's x to the 5th instead of just x? That's right, you do the chain rule. So the chain rule says you take the derivative of the sine part, just like normal, and you get cosine. But instead of plugging in just an x, we're going to plug in that x to the 5th. But then we're not done, because we have to follow that by the derivative of x to the 5th, 5x to the 4th, right? So we're going to use that exact same reasoning back over here. All right? We have something we want to take the derivative of, but instead of an x, we have an x to the 5th. So we're going to write what the derivative should be. It should be e to the something, tangent of 3 something. But instead of putting an x there, like we normally would, what do we do with the sign? Instead of putting an x there, we put in this function that was in the place of x. So we're going to put in the x to the 5th everywhere we normally would have put an x. So instead of replacing all the t's with x's, we replace them all with x to the 5th. But then we're not done, because this is just the first part of the chain rule. We then have to follow it by the derivative of x to the 5th. Does that make sense? So if you have something that's not just a plain x, you're doing the chain rule, you're replacing all of the t's with whatever that function is, but then following it with the derivative of the function. Right, one more here. The derivative of the integral from cosine of t to tangent of t of natural log of x over the cubed root of x to the fifth plus x, or plus 11 dx. All right, so this one's a little weird for lots of reasons. First of all, everywhere we used to have t's, we now have x's. And everywhere we used to have x's, we now have t's. Is that a problem? No, not really, right? We'll just, now the inside function will be in terms of x's, and it's going to go from x's to t's instead. But the other thing that's weird is that we actually have a function on both the bottom and the top and the bottom. So what are we going to do about that? We can't use our theorem unless we have a number on the bottom. What we're going to do is just pick a number, whatever your favorite number is, and we're going to split the integral up at that number. Because remember, we had that theorem that said if you're going from a to b, that's the same as going from a to some other number plus from that number up to b. So we're going to use that fact. My favorite number is 0. So let's just say that now we want to be taking the derivative of the integral from cosine of t to 0 of natural log of x over the cubed root of x to the fifth plus 11 dx plus the integral from 0 up to tangent of t of the same function, natural log of x over the cubed root of 5x to the fifth plus 11. Right. But your favorite number isn't 0? What's your favorite number? Your favorite number is 103. Okay, we'll do it at 103 instead. See, it doesn't make any difference. Just pick a number. Okay. So now what? Now we can take the derivative of each of these pieces separately. And they each have a number involved. Okay? Now the second one here, from 103 to tangent, that one's ready to go. We're going to need the chain rule, but it's ready to go. But this first one, the number's on top instead of on the bottom. So the first thing we're going to have to do is switch them and put in a negative sign. So we're going to be taking the derivative of negative the integral from 103 to cosine of t, natural log of x over the cubed root of 5x to the fifth plus 11 dx, plus the derivative of the integral of 103 tangent of t, and then the same function again. Okay. So, if we want to take the derivative of the integral from 103 to cosine of this mess, we're using the chain rule. Right? Instead of cosine, we're thinking about having a t there. So if we had a t there, we would have just natural log of t, cubed root of t to the fifth plus 11. But we don't actually have a t, we have a cosine. So the chain rule says we're going to plug in the cosine of t and follow with the derivative of cosine, which is negative sine of t. Now we're going to add on to that the derivative from 103 to tangent of t. So we're going to think of it as 103 just a t again. That would have given us natural log of something, natural log of t over the cubed root of t to the fifth plus 11. But since it's not just a plain t, since it's a tangent, we're going to put tangent in those spots and follow with the derivative of tangent, which is secant squared. And notice that I had to bring down this negative sign. And that's it. That's the answer. All right, now we're ready for the second fundamental theorem of calculus. This one's even cooler. This is the one that's going to give you that shortcut for taking integrals. So what this theorem says, before we get that, let's remember, what ways do we already have for taking integrals? We can do the big long way, right? We can do the Riemann sum. we can also find integrals by using geometry to just calculate the areas. But neither one of those ways is very efficient and not really all that fun. So this last way is now going to be to use the second fundamental theorem of calculus. Okay, so here we go. What does it say? It says that if you're taking an integral from a to b, so this is now just a regular, there's two numbers, you're finding one fixed area from a to b of f of x dx, then if you find any antiderivative at all, and you plug in b, and then you take that same antiderivative and you plug in a and subtract them, you're going to get the answer that you want. You're going to find the area between a and b. So as long as you can find the antiderivative of your function, you're set. You know the area. So why does this make sense? Well, this makes sense because that area function, the area from a to x of f of t dt, the area function there is one of the possible antiderivatives. So any other antiderivative that you have, well, so the area function evaluated at b that has to be okay. Okay, so this function, this antiderivative, this antiderivative here, capital F of x, is one antiderivative of little f, but we know another one, right? We also know capital A of x. That's another antiderivative. So how do capital A of x and f of x compare? Capital of A of x is the integral from a to x. F. How do they compare? Well, we talked about this before. If you have two antiderivatives, the only difference between them is a constant. So it has to be true that capital F of x equals capital A of x plus some constant. Okay, so what if we're looking for capital A, f of b minus capital F of a? Well, that has to be capital A of b plus c minus capital A of a plus c. But notice something. Capital A of a, this is the integral from a to itself of f of t dt. And you know that if you take an integral from a number to itself, then it's infinitely skinny. The amount of area that's there is 0. So this is just 0. So you're looking at capital A of b plus c minus c. And plus c minus c, that's just 0. So what this says is that capital F of b minus capital F of a is equal to capital A of b, which is the integral from a to b of f of x dx, or f of t dt, whichever dummy variable you want to stick in there. So there we go. That's telling us that if you want to find this integral, all you have to do is take any antiderivative and subtract f of b minus f of a. All right, let's try this. All right, so here's kind of a summary of all the stuff we just said. We have, if we're reading it this notation, a to b, those are our limits of integration, so that you're finding the area between a and b. The inside function here is called the integrand. X here is the variable of integration, but it's a dummy variable. So you can call it, it could be t instead, it could be s or u or whatever your favorite letter is, as long as whatever you use in f is the same thing you put with the d. And that answer is the antiderivative evaluated at b minus the antiderivative evaluated at a. And that's nice, but it's nice to have a shorthand way of writing that when we're actually calculating. So we write what the general antiderivative is with the x plugged in. Right, so we can just find the antiderivative of little f, write down the whole function, and then we put this vertical line and say we're going from a to b. And that tells us then in our next step we're going to plug in b minus and we're going to plug in a. So let's try it. If we want to find the area under 3x squared from negative 1 to 3, then this theorem says we should find an antiderivative for 3x squared. So what's a function that when you take its derivative you get 3x squared? X cubed, that's right. And if you didn't notice that right away, remember the rule that says you bump up the power by 1 and divide by it? So you'd be saying x squared becomes x cubed over 3, and you already have that constant that comes along. But then those 3's just cancel. So you have x cubed. And we say that's evaluated from negative 1 to 3. So that reminds us we're going to plug in the 3, and then subtract from that what we get when we plug in the negative 1. So we get 27 minus negative 1, or 26. So it's that easy. Instead of having to do a whole Riemann sum, we've got the answer right away. That doesn't mean you forget how to use Riemann sums, because you'll probably have to do them I know you'll have to do them on tests. And sometimes, we don't mention this a lot, but there's a lot of functions that we actually can't find the antiderivative for, or it's really, really hard. And so for those, we still go back to this Riemann sum technique. I mean, we probably have a computer do it for us, and we probably, have it do it with a million rectangles, so we get as accurate as we can. But that's still, that's the default if we can't find the antiderivative. But you can check your work on an exam or something by using this method. Make sure you get the same answer. Okay. Let's try another one. The integral from 0 to pi over 4 of secant squared of y dy. Okay, so what do we got? We've got to find the antiderivative of secant squared. What function has a derivative of secant squared? Tangent. So tangent of y, that's our antiderivative, evaluated from 0 to pi over 4. So now we plug in the pi over 4, we get tangent of pi over 4, minus what happens when we plug in the 0, which is tangent of 0. Okay. All right, so this one actually looks like a sum, right? It says it's the limit as n goes to infinity of the sum I goes from 1 to n of cosine of 1 plus 4i over n plus 4 over, that's supposed to be an n. All right, so that's a sum that they're asking us to evaluate. And we could try to do it, although we have a really hard time because we don't have any shortcuts for cosine. But the easier thing to do would be to recognize this as a Riemann sum. That means that if you were to take this limit, you would get an exact area. But we now know another way to find exact areas using the second fundamental theorem of calculus. So we want to compare this Riemann sum to the general Riemann sum, which is the sum of cosine, well, in general, the sum of a function from a plus I delta x times delta x. Compare that with this Riemann sum that they've given us. So if we compare, it looks like delta x matches up with 4 over n. It looks like a plus I delta x seems to match with 1 plus 4i over n. So knowing that delta x is 4 over n, then the 4i over n matches up with the I delta x, and that means that a is 1. And then what function is this x value being evaluated at? Being plugged into, it looks like this x value is being plugged in to the function cosine. So f of x must be cosine of x. All right, so is that enough information for us to write out the integral? This is the same as the integral from 1 to, well, b. We don't know b, do we? Of cosine of x dx. How do we find b? Well, we know everything we need to know, because we know delta x and we know a. And putting those things together, delta x is 4 over n, but it's also b minus a over n. So 4 over n is the same as b minus 1 over n. So what's b? B has to be 5. So the sum is the same. It's just the sum that's giving you the area from 1 to 5 under cosine of x, which means we can use the second fundamental theorem of calculus. So what does that tell us? It tells us that we can find an antiderivative of cosine, which is sine, evaluate it from 1 to 5. So we get sine of 5 minus sine of 1. Okay, let's try again. We've got the integral from 3 to 5 of 5t plus 2 times t minus 3. Right, so this one's tricky because we don't know how to take an antiderivative of a product. These two things here multiplied together, right? You can't just take the antiderivative of each one separately. That's not the way it works. So the way that we're going to have to do this is before we try to take the antiderivative, we're going to have to multiply it all together. So we get 5t squared plus 2t minus, well, let's just write it out, plus 2t minus 15t minus 6 dt, and we can simplify that. That's the integral from 3 to 5 of 5t squared minus 13t minus 6 dt. So now the advantage to doing that is when things are separated by addition or subtraction, you can do the antiderivative of each piece separately. So if we find the antiderivative of 5t squared, that's 5t cubed over 3, minus the antiderivative of 13t is 13t squared over 2. We're just bumping up by 1 and dividing by it. Minus the antiderivative of 6 is 6t. So there's one antiderivative of this whole function, and then we're going to take it and evaluate it from 3 to 5. So we have 5 cubed. In fact, let me give myself more room here. So 5 cubed over 3 minus 13, 5 squared over 2 minus 6 times 5. So there's everything with 5 plugged in, minus the quantity of the whole thing again with the 3 plugged in. And there you go. That's some big number. You can get out your calculator and put it in if you want to know exactly what it is. All right, and that's it. That's everything we have to talk about for today. So have a nice day.